Just once. You gotta put it on one time.
Like a fish. Okay, are we good, Maddie?
It's recording.
All right. So let's talk big picture in terms of this lab. So as you noticed yesterday, it can be a little bit tough to get good data on this, depending on how you set this up and whether or not you're hitting yourself with a rubber stopper or something like that. So today there's a couple of things we need to do. We're going to finish up, get the data, focus on getting the data, then you can start to do the analysis. So when you get to page 2, right, on that analysis, listen to me, listen to me, listen to me, listen to me, listen to me. There are 4 variables: centripetal force, your mass, v squared, and r. So on any given set of trials, 2 of these are going to stay constant and 2 of them will change. Okay, you just have to figure out which one you're holding constant and which one you're changing. So 2 of them are always constant, 2 of them are always changing. So you're going to draw the 3 graphs. Pay attention. 2 of them start at 0. The first 2 start at 0, 0, and the third one doesn't. Lay out the scale wisely in terms of these graphs. If you want to take a sheet of graph paper, divide it into thirds, that's cool. If you're going to go halves, that's cool. If you want to really kill a lot of trees and put 1 on each paper, overkill, but it's okay. Now, so when you get to questions 4, 8, and 12, listen to me. You want to explain why your graph looks like it does, and you want to mention, again, all 4 variables. Okay? So when you answer questions 4, 8, and 12, they're multiples of 4. Mention all 4 variables: centripetal, mass, velocity, and radius. Okay? So you're going to say, well, because this and this are constant, well, then this goes up, then this has to go up. Or if these 2 are constant, as this goes up, this one has to go down. Something like that. So that's what I'm looking for on questions 4, 8, and 12. When you get to question 13, you're going to calculate the experimental error based upon your data. So what you're going to do is you're going to let the centripetal force be the weight that's hanging down. We're going to let that be the accepted value. So when you get a trial, and you're only going to do this on 4 trials, 4, 8, and 12. You're not going to do this on all 12 of them. You're only going to do this on 4, 8, and 12. So on trial number 4, you had a 0.4 kilogram mass. 0.4 kilograms times 9.8 meters per second squared got you what? How many newtons? 3.92? Okay? So how you're going to do this is, remember, this is an absolute value. It's theoretical minus experimental over theoretical times 100. It's on your equation sheet. So when you do trial number 4, you're going to take 3.92 newtons minus what you get from mv squared over r. So you're going to go to your data. You're going to find the mass of the stopper, the calculated velocity of the stopper at that point, and the radius. This is going to give you a number, okay, which is hopefully something close to 3.92 newtons. Then you're going to divide by 3.92, take the absolute value of that, multiply that by 100, boom, there you go. Everybody's data is different. Show me these calculations. So you're going to have 2 calculations on each one of those. The calculation of experimental error and the calculation of the experimental centripetal force.
What are you calculating?
What? You guys explained it to me.
No, for what? I know experimental error. Centripetal force. All right. What? I see it. It doesn't mention centripetal force at all. One time. I love it. It says add.
Okay.
I can do that for anything.
Now, when you get to the backside on page 3, you're going to go to trials 4, 8, and 12. You're going to calculate the centripetal acceleration using v squared over r. Okay, you're going to have the velocity, you're going to have the radius, boom, there you go. So one of the things we're going to start talking about is g's, in terms of how many times greater a particular acceleration is greater than 9.8 meters per second squared. So right now, you all are experiencing 1 g. Okay? You lift your arms up. You're under 1G. Okay? If you really want to sound like a fighter pilot, ooh, I'm pulling 1G. Okay, great. Everybody is. Get over it. Okay? So, what you're going to do is you're going to take your centripetal acceleration and divide that by 9.8 meters per second squared. So like if your centripetal acceleration is 19.6, 19.6 divided by 9.8 is 2. So you would be pulling 2 Gs. So what that means is if you're the rubber stopper being swung around on the end of that string, when you go to lift your arms, they would feel twice as heavy as they do right now. If it was 10 Gs, they would feel 10 times as heavier. So I'm just having you do that so you get some idea of what's going to happen when we get to that point.
What can the human body withstand?
Typically around 8, maybe 9. Typically most people pass out around 2 or 3 Gs.
I mean like, oh,
Yeah, without passing out, typically it's around 2 to 3. Now, when you get to number 13, excuse me, number 15 and 16, you're going to calculate the centripetal force needed to keep the Earth in orbit around the sun. It's a big number, okay? So on 15, here's the easiest way to do this. Use that centripetal force equals m4 pi squared r over t squared. That's the easiest way to do it. Don't dig around and, oh, I'll find the velocity by itself, and then I'll use that v squared over r, and then I'll get the acceleration, and then I'll multiply that by mass. Just do it all in one fell swoop. Just use that mass, 4 pi squared r over t squared. But pay attention to the units, okay? Pay attention to the units. You want to end up in newtons, which are kilograms meters per second squared. Now, when you get to number 16, you're going to calculate the centripetal force needed to keep someone standing at the equator of the Earth from flying off, okay? So what's going to be different on 16 is that how long is it going to take for the Earth to spin once on its axis? 24 hours, right? So on 15, you're going to use a period of 365 days. On 16, you're going to use a period of 24 hours because it's the Earth spinning on its axis. If you do 16 right, you should get an answer that is much less than the gravitational pull on that person. Okay, which it kind of has to be. In other words, I can't have more centripetal force needed to keep me spinning on the Earth than what gravity can provide. If that number was bigger, none of us would be here having this discussion because we would all be thrown off the Earth because gravity wouldn't provide enough force, wouldn't happen.
what's the number around?
It's pretty small. Okay. Now, when you get to 17, here's the stopper. It's being swung around in a circle. You're going to draw all of the forces acting on that rubber stopper to a relative scale based upon your data from number 1. Okay? So you go to trial number 1, and you draw out, hey, what forces are acting on the stopper? Okay? You're only focused on the stopper. I want it to a relative scale, maybe 2 centimeters equal with Newton, something like that. Don't draw tiny little vectors. So choose a scale where you have a decent sized vector on that one. Okay, so there's that. So stop that, let me hit now. There's a couple of things on this purple sheet, which is due tomorrow as well, that I want to go over. It looks much worse than it is. So let me take you through.
He said it's pretty worse.
Yeah. Okay. So let me kind of get you through some of this stuff in terms of how you can do it. It's up to you. I'm going to show you a couple of options. So let's look at question number 3 on that multiple choice. Okay. So you got a toy airplane traveling in a circle at the end of the guide wires, made to go faster as more wires played out until both the speed and the radius are constant. Double the original values. You want to know what's going to happen to the centripetal acceleration. So there's 2 ways that you can do this. I'm going to show you both ways. Smash mouth physics approach and then a more elegant approach. So one option is that you say, okay, here's this plane, boom, right, flying around the end of the string like this. So one option is that you just do smash mouth physics and you calculate the centripetal acceleration. Now in this case you're talking about velocity and radius. So we're going to use v squared over r. What's the easiest velocity you could pick?
1.
1. Okay? So I'm going to let the velocity be 1 meter per second. What's the easiest radius I could pick?
1.
1. Okay? So if I have an airplane traveling at 1 meter per second and at a radius of 1 meter, how much centripetal acceleration is the airplane going to undergo? 1 meter per second squared, right? Okay? Because 1 squared is 1 divided by 1, boom, boom. Now, what are we going to do in the next change? So we're going to change the situation. What are we going to do to the velocity? We're going to double it. So my new acceleration, what I'm going to call AC prime, because that's going to be the new one, what now becomes my velocity? Now that becomes 2. So that's going to be 2 meters per second, but I'm going to square it. What happens to my radius? It doubles. So now my new radius is 2 meters. So I got 2 squared, which is 4, divided by 2 gives me, so my new acceleration is twice what it was at the beginning. Okay? So if you like this approach, you read a problem like that and you flip out and go, oh, I don't know what to do. Make up some numbers. Okay? I just chose 1 and 1 just because it was easy to work with. Now, that's one way to do this. It's smash mouth physics, but it works. Here's your other option. It's actually easy. So you go, okay, well here's my initial acceleration. V squared over r, right? So what it is, any acceleration is v squared over r. Now, my new acceleration, what's going to happen to my velocity? It's going to get doubled. So how am I going to double my velocity? What am I going to do with my velocity? Multiply it by 2. So this is going to become 2v squared. What am I going to do with my radius?
Double it.
Double it, so that's going to become 2r. So I've got 4v squared over 2r, which becomes 2 times v squared over r. So if I double this side, what do I have to do to my centripetal acceleration? It has to double as well, because it's 2 times v squared over r. So if you like numbers, put in numbers. If you like a more elegant approach, go with this. Okay? All right. Now, one last thing to do and then we're done. So, for those of you that have had chemistry, or at least have had chemistry and still remember, we have this cool deal, which is a centrifuge. Okay? Now, basically what a centrifuge does is you put little test tubes down there and it spins really fast. Okay? And what it does is that it basically creates like a false artificial, or like a false gravitational field. And you use it to separate solids from liquids. Like if you have a precipitate that you want to separate out, you spin it really fast, the precipitate gets pulled down to the bottom. So it gets spinning, okay? Now, so this thing is spinning really fast, okay? So typically, when you have something like this, it's rated in what we call RPM. So this one is rated at about 3,000 RPM. Now, what does the RPM stand for?
Revolutions per minute.
Revolutions per minute. Okay? Revolutions per minute. So what I want to try and figure out is what's the centripetal acceleration of a test tube at the bottom of this. So this thing is sitting here like this. I want to know what's the centripetal acceleration that this thing is going to experience at the bottom. So what I want to use is 4 pi squared r over t squared. Radius will be given to you if that's not a big deal. You can measure that. T becomes a problem. So here's the deal. So as fast as that was spinning, do you think the time for one revolution is a big number or a small number? Pretty small, right? This thing was spinning really fast, so it doesn't take long for each revolution. So, do you think I want to take the 3,000 and put it here for the period? No. Bad. Okay? But what I can do is sit here and go, well, that's 3,000 revolutions per 60 seconds, right? That's what that means, per minute, per 60 seconds. So if I cancel out some zeros, I take 300 and divide that by 6, I get what? 50. Okay? Now I have 50 revolutions per second. Is that the value of period now? No, it's bad. Still not the time. So on your equation sheet, I've got this handy-dandy little relationship that period is equal to the inverse of frequency, which also means that if you cross-multiply, you reverse back, frequency is the inverse of period. So here's the deal. So if you think about it, let's say, for example, I've got this rubber stopper. If I swing it pretty slowly, right, I don't make a whole lot of revolutions per minute, which means that each revolution takes a certain amount of time. Now, if I make it spin faster, now what happens to the number of revolutions per minute? It goes up. So what's going to happen to the amount of time for each revolution?
Goes down.
It's going to go up or go down?
Down.
It's going to go down. So the faster something spins, the more revolutions per minute it makes, the less time it takes for each revolution. So these two values are inverses of each other. So as the number of revolutions per minute gets bigger, which is frequency, anytime you have an event happening per unit of time, that's frequency. Period is how long it takes for each event to occur. So what we're going to do is kind of clever. I got 50 revolutions per second. Is that frequency or is that period?
Frequency.
That's frequency. What I need is period. So what I'm going to do is, to get that period, I'm going to take the inverse of the frequency. So something cool happens when I do this. Well, not really cool, but handy. So if I take 1 over 50 revolutions per second. So I've got seconds in the denominator to the denominator. So what's going to happen? The seconds is going to... So then you get seconds per revolution, which is what period is. So somebody take 1 over 50.
0.02.
0.02. So in this case, I'm going to take the radius, and I'm going to take 0.02 seconds squared. So keep this in mind. On one of the problems on that purple sheet, it's a centrifuge problem. So you've got, on problem number 9, is spinning at 5,000 revolutions per minute. So take the 5,000 revolutions per minute, figure out how many revolutions per second it is, flip it over, that's the time for one revolution. Okay? So that's what you're going to do on that one. Okay, so don't forget, sheet like this, on this purple sheet, I want answers on the left, I want work on the right, I'm done, you're on your own.